Analytics and Predictive Modeling. It's not a name title that you're probably familiar with. A lot of what's in here will be at a very introductory level, and part of that is because a lot of it will be things that you haven't really encountered before. Some very modern ideas and notions that are actually very mathematical. So, we have three goals in this class. The first goal is to explore what it means for a data set to be complex. The second goal is to develop methods used in the data sciences to create predictive models. Goal number 3 is to introduce skills necessary for working with large, complex data. Now notice there's not much mention of theory here. So this is a practitioner course. The structure of the course is that there are going to be 10 modules. The midterm will be after module 6, and there'll be a comprehensive take-home final exam. Each module will have 3 or 4 short videos that kind of kick off the module. Then there'll be some associated readings and exercises. Some modules will have graded assignments, some will not. And there'll be these associated Jupyter notebooks, which will be the subject of the last video. Some of the notebooks will require you to actually do some manipulation and some modification of programs. Some of the notebooks will just simply be like presentations. You'll just work your way through them, and it will teach you in a tutorial fashion what's going on. And there'll be additional support materials on the course site. In particular, the 10 modules is really all you need to know. We're going to start out talking about what is big data, complex networks, nearest neighbors, information, decision trees, metrics, logistic regression, support vector machines, neural networks, and ensemble methods. And that's all you need to know. And you'll only be assessed on the 10 modules that make up the main trunk of the course. There'll also be some additional material. So there'll be additional information, so extra examples, for instance, so extra examples in considering information. There will also be some additional background that you might want to gain. So for instance, complex data comes from complex systems, and I've got a little segment that'll talk about what it means to be a complex system. There will also be some optional materials, especially later in the course, that is beyond the prerequisites for the course. You won't be required to do it, you won't be required to know anything about it, but we'll be looking at softmax and layers. We'll have to get some linear algebra in order to continue, and then talk about deep learning. Again, these are not required, but some of you will want to move beyond what's actually required. Now, grading wise, if you've looked at the syllabus, then you'll notice that the grading is a midterm, a final exam, and individual assignments. And the individual assignments you can attempt as many times as you want to, within reason, because not 1,000 times, but certainly 10, 15, 20 is no problem. And the requirement of the course is that you eventually have to have at least a B on each individual assignment other than the midterm and the final exam. You can make any grade you want to on the midterm and final exam, but to pass the course you have to make at least a B eventually on every individual assignment, no matter how many attempts it takes you to get there. Now, what kind of background do you need? Well, this is a very mathematical course. A lot of what we talk about is sometimes associated with computer science, but if you go and talk to the computer scientists, they tend to associate it with mathematics. And a lot of it is math. So I'm assuming that you know single variable calculus, and everything else we're going to try to develop in-house. Now, this is a practitioner course. The goal is for you as a student to be capable of participating in the data sciences once you've completed this course. And this course has been very successful at that. A lot of your colleagues and classmates who've come through this course in the past are now data scientists. Some of them at startup companies who are making a lot of money, some of them in academia. But a lot of the students who go through this course are now data scientists. So we don't do a lot of theory because we don't want to move too far from it being what I call a practitioner course. So theory will only be as necessary to give you, the student, what you need to be successful. You will have to know calculus, especially limits and derivatives. There'll also be some integrals, but we're actually going to develop most of the integral, area under the curve type stuff in the course itself. But the limits and derivatives you'll need to know, and you'll need to know them conceptually. For example, the question, how can we tell if a function is differentiable given a graph of the function? You need to understand that. That's a very important concept in this course. You also have to realize that most of what we're doing is going to be working with logarithms and exponentials. For example, we're going to work with a thing called information. And information is measured using entropy. And entropy is the average over all possible events or outcomes of the information due to an individual event. So for 0 less than p less than 1, at one point in this course, we're going to have to find the derivative of f of p equals the product p natural log of p plus the product quantity 1 minus p times the natural log of the quantity 1 minus p. So let me show you how you would do that in case you don't remember. So the derivative is the derivative of the entire sum, but we can split that into the sum of two derivatives. Now we have two products, and you might want to remember now the product rule. F prime or u prime, u times v prime is u prime v plus uv prime. So when we apply that, the product rule will give us the derivative of p with respect to p times quantity log p plus p times the derivative of log p from the first product. The second product, the derivative of quantity 1 minus p times natural log of quantity 1 minus p plus the quantity 1 minus p times the derivative of the natural log of quantity 1 minus p. Now the first derivative is dp dp times log p. That's just the natural log of p. The derivative of the natural log of p is 1 over p. And this comes from the derivative rule that the derivative of the natural log of u is the derivative of u over u. Then we have the derivative of 1 minus p times the natural log of 1 minus p. And the derivative of 1 minus p is negative 1. And then we've got 1 minus p times the derivative of 1 minus p. We use our logarithmic derivative again. And we have the derivative of 1 minus p over 1 minus p as the derivative of the natural log of 1 minus p times the quantity 1 minus p. Now let's simplify. We get the natural log of p plus 1. Remember, p is between 0 and 1, so it's not 0 or 1. And then we subtract the natural log of quantity 1 minus p. And then we've got 1 minus p, the quantity, times the quantity negative 1 over 1 minus p. And the 1 minus p's cancel. I get the natural log of p minus the natural log of quantity 1 minus p plus 1 minus 1. And I'm going to use now the logarithmic rules of logarithms, or the laws of logarithms, properties of logarithms. And that's the natural log, the sum of the natural logs is the log of the product. The difference of the natural logs is the log of the quotient. R log, natural log of a is equal to natural log of a to the r power. And notice that that gives me a final result of the natural log of p over 1 minus p. So this is an example of the type of differentiation that we'll encounter in this course. And again, we're going to see lots of exponentials and logarithms. So let me remind you of what these properties are. So there's the properties of exponents. E to the a times e to the b is e to the a plus b. So we'll be using the natural base e, which is 2.718281828.459. I always remember the 1828 because that's year Jules Verne was born. So 2.7 Jules Verne will give you e to 9 decimal places. 2.718281828.459. The other number we'll use as a base is going to be 2. So 2 to the a times 2 to the b is 2 to the a plus b. We'll use lots of logarithms, but you'll find that primarily it's going to be the log base 2 and the log base e, which is the natural log. But these properties of logarithm are very important, and in particular, notice we can go from log base b of c is a log base r of c over the log base r of b. So we can switch from one base to another with logarithms. So for example, if I've got e to the x over 2 over the quantity e to the x over 2 plus e to the negative x over 2, I can multiply both sides, the top and the bottom, by e to the negative x over 2. I combine the exponents, and that gives me 1 over 1 plus e to the negative x. This is actually something we'll see later on. The derivative of e to the x over e to the x over 2 plus e to the negative x over 2, well, that's kind of a mess. But we can simply take the derivative 1 over 1 plus e to the negative x because we simplified. That's the negative of the derivative of 1 plus e to the negative x over 1 plus e to the negative x squared. And that gives us our derivative e to the negative x over quantity 1 plus e to the negative x squared. Now, other than the calculus, we'll develop the rest of the math in the course. So we'll have graph theory as a tool for analyzing data. We'll see that. We'll see some basic linear algebra, but mostly notation and the summation symbol. So k equals 1 to n of x of k is x1 plus x2 plus x3 all the way up to x sub n. So the summation symbol will be important, and we'll be talking about vectors and matrices, but mainly just notation. So for example, suppose we were working with the data set. We had a table of data. It has features, and it has a certain collection of observations. And notice that we're starting our indexing at 0 instead of 1. So notice that this is actually a 0 and a 1. So this is because we'll be using Python, in which case indexing does that. And this table of data can be thought of as an array, Dij, where Dij is the value of feature j associated to or given in observation I. So we can think of these entries as having this notation. And that would be important because typically the m and the n, the number of features and observations we have, those tend to be very large. So we would never want to start writing down all the numbers in order to do something. Now we can also think of observation, each individual observation, as a vector. So the row here, which is observation 0 of all these different features, we can think of as an actual vector. Now, that's really the most linear algebra we're going to do. So suppose we have a function y equals f of x1 up to xn, where each of the x sub j's are functions of t. Well, then actually y is a function of t. Its derivative, using the chain rule, dy dt, is the sum k equals 1 to n, the partial of x sub k, partial of f with respect to x sub k, the derivative of x sub k dt. looks like the chain rule. And often we will simplify this using a dot product. So if A is A1 up to AN and B is B1 up to BN, then A dot B is A1 B1 plus A2 B2 all the way up to A sub n B sub n. Or writing it in summation notation, K equals 1 to N, A sub K, B sub K. So we will see linear algebra, but just in this very simple sort of representation as notation, and anything beyond and even the notation will develop in the course. So what does this mean? This means instead of having to write y equals f of a whole bunch of things, we can simply say y is f of the vector x of t, where x of t is the vector x1, x2, x3 up to xn of t. The derivative then can be written as a dot product, where df dx is just all the possible partial derivatives, the gradient. There'll also be some lines and planes, and you'll have to know equations of lines and planes. That's pretty basic. But no explicit linear algebra. This really is the extent of what we'll be doing with linear algebra. So you might ask the question, quite naturally, why? Why is there not more linear algebra? And the answer is, first off, that's a very good question. You might expect large data sets to require lots of linear algebra. There are a couple of answers I want to give you. First off, networks and calculus via optimization can really be used to reproduce what we get from linear algebra. So we don't need the linear algebra if we're using networks and calculus. The linear algebra is sort of built in without having to do it explicitly. The second thing is, if you know a little data science, a little predictive modeling, you can probably get a job, have a nice career. Because data science is working with data that has a lot of information in it, and the ability to pull that information out at any level is really useful. But a little linear algebra just tends to get you in trouble. The reason for that is there's the concept of a condition number of a linear transformation. And until you understand the concept of conditioning of a matrix, linear algebra in the data sciences can lead to overfitting, instability, lots of other issues without your having a clear way to deal with them. So unless we're going to do a lot of linear algebra, it's probably best not to try to do much of any linear algebra. Now, so what does that mean? We're going to become practitioners in data science. And so that means we're going to have the ability to use abstract mathematics conceptually and concretely. Because we're going to have to tell a machine what to do with a large set of data. We're not going to want to do it ourselves. These are very large data sets, hard drive size data sets. And we'll also have to assess what the machine does. Very important that we be able to look at what the machine produces from the data and determine whether or not it's any good. Probably 90% of the data science jobs are exactly that, assessing how good the results are. We're also going to have to use computers. Now, we're actually going to have to use computers quite a lot. We're going to use packages written in computer languages. And there's very good reasons to avoid the use of GUIs and mousing around and clicking on files and menus and stuff like that. So it may seem like that's going to be pretty in-depth as far as programming. However, data science really only requires basic programming skills. Now, this is actually some of the biggest names, Andrew Ng, Nando De Freitas, people like that. When they teach these courses, they emphasize it's math, it's not programming. So data science really only requires basic programming and a lot of math. At least for an introductory course like this one. Of course, there are always going to be occasions where the programming can be intense, but certainly not in this course. So data science is math more than computation. and more than programming. That's one of the things that you'll find out in this course. So what do we need coming in? Well, the ability to use basic math and calculus abstractly, willingness to work with a computer. You'll be given these notebooks containing programs and explanations of how to use them. They'll be mostly in the language Python. A few of them will be in the language R. You'll need to learn the basics of Python R, but nothing advanced. We will not be doing even intermediate Python and R. You'll simply be modifying and interacting with already prepared notebooks. So what's next? Well, next you have to set up an account at Sage Math Cloud, and that's cloud.sagemath.com, because this is where we're going to be running our notebooks. These are called Jupyter notebooks, and you've got two sample notebooks, one for Python, one for R. Be sure you do the Python one first. The Jupyter notebook is a single format for several different languages. It means that you can have access to many different languages using the same approach, the notebook. So that's Julia, Python, R, Haskell, Lua, many of these. And we try to keep everything very close to this notebook format, even when we're using different languages, because it means that you can move back and forth between these languages with relative ease, something that was almost unthinkable in the past. The Sage Math Cloud will be all that you need. It's free. It runs everything. Everything's already installed except for some of the data sets and the notebooks. You'll have to actually upload those. However, there'll be options for local installs once the course begins, if you want to run things locally. But I want everybody to have a Sage Math Cloud account, and that kind of be the center for what we do, even if you're running things locally. So let's move on to the next video, setting up a Sage Math Cloud account and getting started with these two sample notebooks.